All right, now that we've figured out how to draw an interaction diagram, we are going to begin using pre-made interaction diagrams to select a column design. First, let's talk about a column type. Here we have 3 different column types. We have a circular spiral, right? You're not going to have a spiral in a square column because spirals are generally in a circle. So that's a spiral circular column. Then we have a square or a rectangle. These are both squares, but square with reinforcement on 2 sides, on 2 faces, or put down there a square with reinforcement on 4 faces. You can tell they have this bending axis drawn. Now for the spiral and for the square, with that looks the same on all 4 sides, the bending axis doesn't matter. Obviously the bending axis matters with 2 faces because you assume you're bending about an axis like that rather than the other way around. Because that way we have our reinforcement on a tension face. This diagram would be much better in color. Here, let me see if I can. I'll change this color. All right. Alright, that's my bending axis that we have on that. So in this diagram, we are looking at columns that have three different column types, but they have the same area of steel. And the same gross cross-sectional area. It's a G. And we're going to see how they perform differently. We're going to look at the ratio of the eccentricity to the cross-sectional dimension H. E is our eccentricity of our axial load. it's equal to our moment divided by our axial load. And H is the cross-section dimension, like diameter or width, height. So here we have our E over H less of 0.1. So that means we don't have a lot of eccentricity. Right? And what performs the best there is our spiral. So spirals are better at E over H less than or equal to 0.1. Why is that? If they have a really low eccentricity, that means they're mostly, they have a high, right? We're looking at high axial load here. And the phi for a spiral load or a spiral tied column is 0.75 versus 0.65 for a regular tied column. That's why your spirals are better if you're going to have a really high axial load and not a lot of moment related to it. However, spirals cost a lot of money. You're usually only going to see those out in, like, I don't know, high seismic regions maybe. Now, if we have a higher eccentricity, like over 0.2, here we, right? Let's see. Right, here we have our 0.2. What's going to be better for that? Kind of makes sense. Reinforcement on only two faces. A higher eccentricity means you have a higher moment load. And what's going to take care of that is if you have reinforcement concentrated on the two faces as opposed to distributing some on the other two faces. So square reinforcement with reinforcement on two faces, that means your reinforcement is out on the edges here, providing your moment capacity, right? Because your phi mn is your area of steel. Times Fy times that distance. So those are better, right? We can say because of that, a square is better. A square with reinforcement only on two faces is better for eccentricity over height greater than or equal. Oopsies, did I make sure I said less than? Okay. Greater than or equal to 0.2. And you could even make it rectangular. For more moment capacity, right? If you make it rectangular, you're increasing that moment arm between your tensile reinforcement and your compression block. So if you increase that moment arm, you increase the moment capacity. So where does that leave? Square on fourth faces? Well, they're just the easiest to construct, right? Especially if you have your E over H less than 0.2. So if you have a really high moment, you're going to want to distribute that reinforcement to only two faces. But if you're in the middle, if you have less than 0.2 for your E over H, just do a square with reinforcement on four faces, unless the architect or the owner, somebody really wants that spiral. Unless it's really justified to. I mean, maybe it's justified cost-wise, but stick with the square on four faces if you have E over H less than 0.2. If you have a high moment requirement, you're going to move to a square or even a rectangle with reinforcement on two faces. So column design, if we're going to choose our material properties, our F prime C, we want it to be equal to or greater than that of our floors. And our yield stress for our steel, we want grade 60. For our longitudinal, spirals, and maybe our ties. And you could use grade 40. For your ties. That's similar to beams. We want grade 60 for our longitudinal reinforcement, but our ties could be grade 40. So like our shear reinforcement, basically. our reinforcement ratio, if we go to section 10.6 in the ACI code, it's on page 158. This is all about reinforcement. So for non-pre-stressed columns and for pre-stressed columns, which we're not doing, the area of longitudinal reinforcement shall be at least 0.01 of your gross cross-sectional area, but shouldn't be greater than 0.08. So you're talking 1% to 8% of your gross cross-sectional area. All right. Let's see. 0.01. 0.08, right, where your row is your area of steel over your gross cross-sectional area. For rules of thumb, generally 1 to 3%, so 0.01 to 0.03 is your most economical, and 3 to 6% is your maximum to allow for splicing, lap splices of reinforcement. Right, you're gonna have to splice your longitudinal bars. So 1 to 3% is about what you're gonna want. Estimating our column size. If we go back to our phi-pn max equation, let's go back to that. if we go back to that and we write our phi PN max is for column, for ties, right? If we do the 0.8 times the 0.85 and use the 0.65 for ties to get phi PN max, and do some finagling with replacing that area of steel with rho. You can sort of simplify it to give an estimate of where to start. So, did all that for you, didn't but basically, if you have a tied column, your AG is your gross cross-sectional area as a trial. You want it to be greater than or equal to your required PU, 0.4 F prime C plus your Fy times your rho of your column, right? Like say 3% or something like that. 0.03. And for your spiral columns, your AG trial is going to be a little bit bigger, or no, a little bit smaller, because it has a higher phi factor. So you can get away with less, right? F prime C plus Fy rho of your column. Now this will right, we're only looking at your load, axial load. So it will underestimate your size for columns subjected to high bending. And generally, we want a 10-inch by 10-inch. Let me draw that better. Tied column or a 12-inch diameter spiral column minimum. So slenderness in steel design, right? We had to talk about slenderness, and we wanted to brace it, for buckling and all that. So ACI talks a little bit about slenderness. It's on that slide right there, but on page, it's 6.2.5, page 68. All right. Oh, look, there's alignment charts. Slenderness effects shall be neglected if A or B is satisfied. If we're not braced against side sway, right, that means if we're like our little, I can draw that on the next one, but, right, our building can go like that. If our building is like that, it's usually like an X column or some X brace. This would be a moment frame, right? As long as we satisfy these requirements, we don't have to account for slenderness. So this is, all right, let's see, 6.2.5, do not need to account for slenderness if A or B. Again, not braced against side sway, that means we're in like a moment frame. Braced against side sway, braced frame. And then it talks about M over M1 is negative if the column is bent in single curvature. Single curvature would look like that. Double curvature would look like that. Right, 2 curves, 1 curve. All that to say, we will stick to short, non-slender columns. So that we don't have to account for slenderness. So longitudinal or reinforcement detailing, let's see, cover requirements. Are the same as beams. That is in ACI 20.5.1.3. Hopefully you have that tabbed. So generally you're like, what, 1.5 inch cover. This may increase, let's make a note. With fire code. Right, maybe 1.5 inches is what ACI requires, but the fire code says 2 inches. So that's something to pay attention to. For your number of bars, this is 10.7.3.1. For non-pre-stressed columns, the minimum number of longitudinal bars shall be 3 within triangular ties, makes sense, 1 in each corner, 4 within rectangular or circle ties, 6 if they're enclosed by spirals, or for columns of special moment frames enclosed by circular hoops. So you need at least 4, 1 in each corner, for rectangular. Circular ties are not spirals. Circulars are discrete versus spirals are a continuous spiral, like a slinky. Let's see. Minimum spacing is still the same as well. Is ACI 25.2. Which I believe is just the same as beams, right? We have our minimum spacing of reinforcement. Oh, that's longitudinal reinforcement. No, it's not the same. But it's in this. It's right. This is for horizontal layers, so this is for beams. Columns. Oh, we increased our minimum to 1.5 inches. 1.5 times the bar diameter, or 4/3 D aggregate. Whereas beams before were 1 inch, now we're up to 1.5 inches. 1 times the bar diameter, now 1.5 times the bar diameter. That is the same. So 25.2.3. Right? Whereas beams was 25.2.1. It's the maximum of 1.5 inches, 1.5 times the bar diameter, or 4/3 the diameter of the aggregate. So in terms of the transverse reinforcement, that was the longitudinal, right? That provides our axial capacity and our moment capacity. Ties The reasons for ties in columns. To prevent the buckling of the longitudinal reinforcement. The longitudinal reinforcement is in compression. When we have something in compression, it might buckle. If we brace it with the ties, that decreases the length over which that can buckle, right? If we have like that, it could buckle there, versus if we add another tie, now we've shortened the length over which it could buckle, right? Those are longitudinal up and down and ties horizontally. Other reasons for ties are constructability. Right, so they're not just flapping out there in the breeze. Kind of strengthens, stiffens our reinforcement in general. It does provide ductility. I talked about this a while back, because it confines the concrete core. And then also the same reason that we have ties in beams, shear reinforcement. The main purpose is to prevent buckling of our longitudinal reinforcement. If you require ties for shear strength, similarly to beams, you may have some shear. You must comply with ACI 318 25 .7.2. That is column buckling requirements, which we're going to talk about on the next slide. So that's to prevent requirements. That's to prevent buckling. And you must comply with 318. I probably should have been putting that before. 10.7.6.5, which is column shear, similar to beam shear. So if we look at 25.7.2, this is our column reinforcement. The first part, this is about the spacing of ties. How close together they need to be, or how far apart they can be. And then this second part is about the size. If you have number 10s or smaller, you can use number 3s. If you have larger than that, number 11s or larger, you have to use number 4s. So this is on page transverse reinforcement. Is on page 499. It literally just looks like exactly what I have here. And then it gives examples of what kind of ties you can put. And then this is the buckling, right? If we're looking at column shear, we have spacing requirements. This should look similar to beams. Those are 10.7. Looks similar, OC, but it's about columns instead of beams. Anyway, so that's the maximum spacing for shear reinforcement. Obviously, you have to calculate how much, right? So you have to satisfy both of these if you have column shear, basically. If you don't have any column shear, you just have to satisfy the buckling. Spirals, a spacing, clear spacing, that means the distance between the spiral has to be at least 1 inch or 4/3 and could not be greater than 3 inches. the spiral bar diameter has to be at least a number 3. Then it gives a ratio of how much spiral reinforcement you need based off of your dimensions. We're not going to really get into spirals. We're going to stick with ties. But there you go. So let's talk about the column design process. You're going to select material properties, or they might be given to you. Right, F prime C and Fy, and a trial reinforcement ratio, which we said needs to be between 1 and 3%. And from that you can select a trial size. Right, a gross cross-sectional area. Gonna figure out which type of column you want to type based on EH ratio, right, our eccentricity. And you need to ask yourself at some point, like I said, in this class we're going to not deal with any slender columns, but out in the real world you're going to have to double check that. Okay, so we selected our trial size. We're going to be using some design aids. And they look like, where'd it go? They're in the back of your book. Oh no. That don't happen. So we're going to use these design aids. This is page 1094. That's where they start, on the back of the book. And you see we have a potentially rectangular section with reinforcement only on 2 sides, so this would be something maybe with a higher moment. We have an F prime C and an Fy, and this gamma, which the gamma is the distance between center to center of your longitudinal reinforcement divided by the overall height, right? So the distance between the center to center is 60% of the overall height for this specific design aid. And then we have reinforcement ratios, P rho G, that's just your gross cross-sectional area G. For this would be the 0.5, this would be 0.4, and you're following along. Here's where you have no stress in your steel, half of your yield stress, compression limit, tension limit, and your E over H. Keep trying to do that, doesn't work. Your moment over your BH squared. This is a non-dimensional, or no, it's in KSI. So it's your basically a stress, and your VPN or your M or your PU over BH. So stare at this for a little while. So we're going to use, these are the design aids that you can use. So this is our design aid, and we need to know, these are all based on your F prime C, your Fy, and this gamma. Assuming your F prime C and your Fy, right, that says E, that's our 4 KSI, our 60 KSI, and our 0.6, right, our F prime C, Fy, and that gamma. So we want to know our gamma. So that's our next task. Calculate gamma. That is our center to center distance between longitudinal bars and overall depth. All right, if we're looking at, just draw that picture that we just had. I don't know. Right, if our overall is H, our gamma, that's in the center, doesn't look like it is, but is gamma H. Right? And we could get that by, what do we need to subtract, right? Our gamma H, estimating it, is our H minus our cover on both sides minus the diameter of our stirrups on both sides minus 2 half bar diameters. Right, I don't have my stirrups in there, but right, they would be like that. Right, so you take your height, you subtract the cover, you subtract your diameter of your stirrups, and your 2 half bar diameters. Let's go back and we'll say that that is rho G, because that's what the book uses. It's just your ratio of your column. Let's see. You can go back and check this one too. There it is. Make that a G. I had that in my notes, but I couldn't figure out what the G was for other than gross. I don't know. So, okay, so we calculated our gamma. Is that number 5? Okay. Number 6, we're going to use the interaction diagram to determine that G. We have a guesstimate, right? So we know our F prime C, our Fy, and our gamma, and column layout. Our correct interaction diagram. And then use our required PU and MU to select on that interaction diagram to determine rho G. And if you recall, we're looking at this one. It's actually, this would be PU over BH or MU over BH squared. Sometimes it's like that, sometimes it's not. So let's make a note in textbook. Use PU over BH and MU over BH squared. Right? That's what it said, right? BH squared, yeah. Do I have it? I don't. If you go and look at the FE handbook, this is the one that you will use when you're taking the FE starting now, which is, it was new as of July 2020. There it is. Let's see, where's the civil? Civil starts at page 259. Oh, I guess you could do the Alt F, right? Or Control F or whatever. geotech, structural analysis, structural design. There we go. Here's an interaction column. C for the thing. They use a non-dimensional thing where it's PU over phi F prime C AG. So they take out the stress is what they're taking out. Or they have another one. This is like the textbook, which is literally from our textbook. So there's two different ones. This one is from a different textbook, that's why. So just keep in mind what it's looking for, right? This one has the eccentricity in it. Well, because mu equals pu times e. So that's why. So those are two different ones. Those are the two different kinds in the FE reference manual. PU over phi F prime C AG and PU times E over phi F prime C AG. Of course, then you kind of have to guess a phi, which conservatively you could use the 0.65. Because it's more likely to be 0.65. Oh, AG times H. There it is. Okay. Okay. That's a 7.5. 0.65 or 0.75, right? 0.65 is ties, 7 tie is spiral. So you go to your, here, I'll give you a minute to make sure you write that down. Right, so you would go to, let's see, this is the one, well, this is one of the ones in your textbook, right? We have a f prime c of 0.4, an fy of 60, and a gamma of 0.75. And we find, and we use our coordinates, okay? We know this value and we know this value, so we find the spot on the chart and we look, okay, that is between it's like halfway between 0.04 and 0.03, so I would choose rho equals 0.035. All right, just make your best guesstimate. What it looks like. And that is how we determine our reinforcement ratio for a column. Now we said 1 to 3 was what we wanted. right? Our goal was like 1 to 3%. If rho G is greater than about 3 or 4%, increase your section size. And calculate everything again and pick a new row, right? If rho G is less than 0.01, use 0.01 or decrease your section size. By section size, I mean your height and width, or your side. If it, if it's square, you only have one value. But keep in mind slenderness, right? If you decrease your section size, you're more likely to be slender. Our next thing, so we have to select reinforcement, right? Longitudinal reinforcement. Right, our area of steel is equal to rho times our gross cross-sectional area. So we get an area of steel, we select how many bars that would be. You're going to want, obviously, even distribution. Now that you have that, calculate your capacities. Just remember that cap on your axial capacity. Nine, select your ties, which that was, if it was a 10 or less, it could be a number 3. Beyond that has to be a number 4. And the spacing, I guess this one here, you also have to check your spacing, right? Your detailing requirements. Select our ties, size, and spacing. It designed for shear if necessary. That's kind of a afterthought. It's not going to change your longitudinal reinforcement, but it might change your ties. And that is it. That is how you design a column. So the next thing we're going to do is an example. And yeah. Okay. Thanks.